Rightio, so welcome along. We're going to do January 2013 Rings, Polymers and Analysis. And we start off with question 1. And we need to explain why pyric acid is soluble in water using a labelled diagram. So hopefully you can see you've got a nice acid group there, and you know from your carboxylic acid chemistry that these guys hydrogen bond. So if we draw out the acid group there, then we are going to make our hydrogen bond. Make sure it ends up on the lone pair of your water molecule there. Know that from AS chemistry. That's delta plus, delta minus, delta minus. You can do these guys if you like. That's your hydrogen bond. Then that bond angle there should be 180 degrees. And then really in terms of your explanation, really you're going to say that the acid will hydrogen bond with water. And that should get you your 2 marks. Right, so we're now on to a synthetic question, and we can prepare this by reacting propane 1,2 diol. So propane 1,2 diol is of course that boy there. With excess acidified potassium dichromate, which we know we represent with just square bracket O. That is going to give me the acid, which is that boy there. Now, secondary alcohol has gone to a ketone group there. Primary alcohol here has gone to a carboxylic acid here. So I need 3 square brackets O, and I'm also going to make water, and I need to make 2 waters. One for this guy to become a ketone, and then one for this to become the aldehyde, which takes care of 2 of those O's, and then the final O is to pop in there to give me my carboxylic acid. Right, so we now want a mechanism. It can be reduced by sodium borohydride to form that molecule there. Now you can see the acid group is the same, but this ketone has become back onto a secondary alcohol mechanism. So you know that this produces the hydride. So that needs to be delta plus, that needs to be delta minus. This goes straight into that carbon atom there. The bond breaks, so make sure the arrow is in the middle of the bond, go into that oxygen there, which is delta minus. That gives me the intermediate, like so, and it's done in water, like so. So that goes to the hydrogen, and that goes there to give me the molecule that they want us to make, whoops, plus OH minus water. Right, so now they want me to describe a chemical test that's going to distinguish between compound A and the acid. Now if we whiz back and have a look at the acid, you'll see that's the same. That is a ketone there. However, that ketone has become an aldehyde here. So you would use Tollens reagent, and you would see a for compound A silver mirror would be produced. Because aldehyde group is oxidized to carboxylic acid, no reaction with pyruvic acid. This is a redox reaction reaction. Organic product formed is going to be actually the diacid, because that aldehyde group there is oxidized into a carboxylic acid group there. Right, okay, so we're now moving on to part B. Compound B is an organic compound, giving me the element analysis and the mass spectrum, and it wants me to determine the molecular formula of B. This isn't too difficult, is it? Let's do it up here. You've got carbon, you've got hydrogen, you've got oxygen. This is from your AS days. You divide by the relative atomic mass for each of those. I'm going to cheat here. That gives you 4.65. That will obviously give you 7.02. That gives you 2.32. You divide by the smallest one, which is that one. That's going to become 1. The carbon's going to become 2, and the hydrogen becomes 3. So my empirical formula is C2H3O. If you add all that up, you realise that it's actually half the molar mass which is coming in there. That is at 86 peak. So this will come to 43. So you need to times that by 2 to give you C4H6O2. So I now need to work out what compound B is. Right, it's an E stereoisomer, so it contains a carbon-carbon double bond. It effervesces with aqueous sodium hydroxide, that's sodium carbonate. That's telling me that it's got a carboxylic acid. It decolorizes bromine, well, that's telling me it's got a carbon-carbon double bonding, and it polymerizes. Well, okay, I know it's got a carboxylic acid, so again, that's giving me information about the carbon-carbon double bond. So I have got 4 carbons, so let's just sketch this out. I know I've got 4 carbons, I know I've got a carboxylic acid group. Yeah, I know it's an E isomer, so my double bond has to be in the middle there. If it's at an end, I wouldn't have any type of EZ isomerism. So it's going to be along the lines of that point there. I know the stereochemistry because it's told me it is the E isomer, and therefore the H's are going to be on opposite sides. Right, so compound C is where it effervesces, so that is going to be my acid group reacting to give me the sodium salt, the carboxylic acid. D is where it adds bromine across this bond here. So I'm going to draw it slightly oddly, so you can see how I'm putting bromine on the end there. And then the final one is when I make my polymer. So remember, to do your polymer, if you redraw that as an H shape, like so, and then, so you just pull that out, that's your H shape there, and then the double bond, which was there, just opens up like so. And that's 1 working unit of polymer E. Right, so moving on then to the next stage. Let's go back to full size. Developing an azodine, got it there. First stage, I've got methyl benzoate being nitrated with concentrated nitric acid. Let's do the mechanism, showing how this behaves as a catalyst. So first of all, let's go, give myself a little bit more space. So I'm going to show how my nitric acid reacts with sulfuric acid to give me my NO2 plus H2SO4-. No easy way about this, guys, you've got to learn that one. Right, now I'm going to do my mechanism. Notice I substitute here. So, it doesn't matter too much, the electrons are going to come out there to go to the nitrogen, but when I draw this, I've got to break the aromatic ring against that carbon there. That carbon has to be where the ring is broken. Then that bond breaks to go back into there to reform my 6 electrons. I formed H+, and then the final step is H+ reacting with that bad boy there to give me my sulfuric acid back, hence showing how it acts as a catalyst. The name for that mechanism is, of course, electrophilic substitution. Right, I've now got a mega flowchart here. I've got to get to this, I've got to get to an azo dye. If I just show where it goes through, goes down to this azo dye here. Before I get to it, I've got to get to this boy here through a step. Now obviously that's my diazonium salt there, that's a nitro group there. The intermediate, if you know your synthetic diagrams, is that I have got to go through the NH2 group there for reaction 1, and then I can turn that into my diazonium salt. Now I'm going to move on to the next page. It says suggest the reagents for reaction 1 and reagents conditions for reaction 2 and 4. So reaction 1 is going from nitro to that, so that's going to be tin in concentrated hydrochloric acid, which you need. For reaction 2, I'm making my azo, so my diazonium salt there. So you can use NaNO2 with HCl, and you need to do this below 10 degrees C to get that one to work. And then finally, they want reaction 4. So reaction 4 is taking my diazonium, my diazonium azo dye here, going in spring long weekend, being to go to here. So what am I changing here? That stayed all the same. It's just that group there. That is, of course, ester group. I've hydrolyzed that, and I've made the sodium salt. So to do that, I've obviously used sodium hydroxide solution to get that one to work, and I would have heated that as well. So key things really to include is you've got lone pair on nitrogen atom is delocalized into the benzene ring. This increases the electron density of the benzene ring. Electrophiles are more polarized and more attracted to the ring. So you should have covered all the main points there.